Okay, so we're gonna finish off worksheet number 9. We had already started this page, so you haven't seen it. Just make sure to screenshot these pages. But we just started on a couple of the reactions and wrote a few notes, so that's how we're gonna be approaching everything. We're going to be writing a few notes and then doing the mechanisms. But honestly, if it takes too long, I'll just do the products for some of them, and I guess for the starting reactions, I'll do the mechanisms. So we're going to start off with sulfuric acid. So the notes that I would write down for this are, it's an E1 mechanism for secondary or tertiary alcohols. And then E2 for, as you would guess, for methyl and primary alcohols. Okay. And so I guess the first thing, because if you ever forget what these things do, always look at, do I have an acid? And for most of these, you are going to have an acid. Here, we have an acid. It's a sulfuric acid. And so write it out to where you can see the acid and base arrows. But again, whenever you see an acid, we're thinking first step, protonate. And so find your base, which is going to be your electronegative atom, oxygen. And so from those electrons, you're going to draw your arrow, because that's your base, and you're going to grab onto the proton, which is the hydrogen that is the most easily able to pluck off. So the one that we wrote out. And again, I wrote sulfuric acid in this way so that I can show the bonds breaking, because these are all arrows that you should be showing. And so now I have a really good leaving group, because when it leaves, it's going to be neutral. The next thing that we'll do is, again, you have your alpha and you have your beta carbon. And I'm looking at the hydrogens to deprotonate, because this is E1 or E2. So they're on your beta. We have a hydrogen that we're going to deprotonate. So I'll write it out so that I can show the electrons are my base, show bonds breaking, show leaving groups leaving, and I'm doing it all at the same time. I'm doing an E2 mechanism for the reason of my alcohol, the OG alcohol over here, it being primary. And so this was the E2 mechanism. That's why everything's happening at the same time. And again, the double bond is only going to form between the alpha and the beta carbons. And so you should just look like this. Perfect. I guess I'll also put watch out for rearrangements. It's something I hadn't included in my original notes, but I mean, if you have an E1 mechanism where you have a carbocation, that means that you're able to do rearrangements. And so on the second one, I purposely did the same kind of mechanism so that we can show or see if we can do any rearrangements. So again, same thing. Base grabs onto proton, proton breaks off. We now made a good leaving group. And this one is different because it's secondary, and so since it's secondary, we favor an E1 mechanism because we're able to make a stable carbocation. And so in E1, you have to make that carbocation by making the leaving group leave by itself. And so we have that carbocation by itself, and now, again, every time you see a carbocation, think to yourself, can I rearrange? Can I put this carbocation in a position where it's more stable? Right now, it's a secondary carbocation, but I'm going to look at my kind of beta hydrogens. If I move this beta hydrogen over to this side, then I'm going to make a primary carbocation, and that's something that we know isn't pretty much possible. But if I move that other beta hydrogen over, and so you go from the bond to the carbon that you're moving that hydrogen to, when I move that hydrogen over, I put the carbocation in a tertiary position, which is more stable, and so it's perfect right here. Again, find your alphas, which is where your carbocation or your leaving group was, and find your betas, which is 1 carbon away. And so in between all of these alpha and beta carbons, that's where a double bond is possible. And if they're asking for the major products, it's kind of obvious to see which one it'll be. But if they just ask for all products, then you're going to have to deprotonate the hydrogens for each one of them. I'm going to do the deprotonation from the one that's going to give me my most stable product. So I'll draw out that hydrogen from my base. Those electrons, they break off. And then bond between carbon and hydrogen breaks to make a double bond. And so again, this is what would make my most stable alkene, just because it's tri-substituted. So that means that there's 3 R groups around my double bond. But you would also have what I'm pretty sure will be a di-substituted alkene as your other product if you had deprotonated either one of these. And they would be the same product again because they're chemically equivalent. And so you would have 2 products. One is tri-sub and one is di-sub. This one being your major. Again, the things to take away from this is every time you see an acid, protonate, and that usually makes a good leaving group, and then assess whether or not, like what the mechanism is for your reaction. So for these types of reactions, it's E1 when it's secondary or tertiary alcohols. It's E2 whenever it's methyl and primary alcohols. If you do have an E1 mechanism, if that's what you identified, then make sure to look out for rearrangements. Is it possible to put my carbocation in a position that it'll be more stable? But those, again, they'll have the same notes because they're the same reaction. They just happen to be on different amount of carbons. Next one, POCl₃ and pyridine. So this one is a forced E2 mechanism. That means you don't need to look out for rearrangements, but you do need to look out for antiperiplanar arrangements. So if they ever give you stereochemistry, you would know how to go about that. But antiperiplanar just pretty much means that, let's say Cl, that your leaving group and your beta hydrogen that you would be deprotonating, they would be on the opposite sides. Yeah, that's as far as I'll go with that. So you can do a little quick refresher on that by yourselves because it is still important, but let's begin with the mechanism. Let me think about this. Again, I think I should start giving you tricks to this. The trick to this one is, again, identify your alpha and identify your beta. Your double bond has to be between the alpha or the beta, and so you would have 2 products. Between the alpha and between the beta, and then obviously one of them is going to be major. It's the one that's more substituted. But that's how you pretty much identify, like, what's the reaction, or what are the products fast. Identify alpha, identify beta, and do double bonds between alpha and beta. And that only works for E2 mechanisms because if there's an E1 mechanism, that's where you have to be a little bit more careful. Okay, let's begin with this. Write out what POCl₃ looks like. Here, our electrophile looks a little bit different because we just haven't seen this before, but just notice how on phosphorus there's a whole bunch of chlorines and oxygens that are pulling electron density away from phosphorus, and so our most positively charged atom in that compound is going to be phosphorus. And so you identify your nucleophile, which would be your electronegative atom on your original compound. Your nucleophile will attack your electrophile, and when you make a bond, you have to break one, and so leaving group would leave one chlorine. Okay, the next thing that happens, you write everything from scratch. That's where it gets a little tricky. But you didn't do anything with that hydrogen, so leave it there. connected to phosphorus, connected to chlorine, connect that, or do the double bond phosphorus right there. And so right now, I guess I forgot my charge right here. Next thing you would do is you would use pyridine. So you can rewrite it, or you can just grab it from over here. I'm gonna grab it from over here because I'm lazy. And you just deprotonate. I haven't been doing it this whole time, but I think it's very helpful what steps you're pretty much saying. So like this first step would be nucleophilic attack. The next step would be deprotonation. The next step would be you made your good leaving group. And so that means leaving group leaves. And so let's see what the leaving group looks like. It's just this neutral compound right here. Neutral compound right here. Let me draw that a little clearer, or just smaller. Okay. So what happens from here? This right here is your good leaving group. And it's a good leaving group because you're going to make very stable bonds whenever this leaves. So phosphorus-oxygen bonds. Pyridine is going to come back. You are going to deprotonate the beta hydrogens. So I'm just going to do any of the beta hydrogens just for an example. You're putting the electrons from that beta hydrogen onto where your double bond should be, and then your leaving group leaves. And so you'd put the electrons onto oxygen. And then you'd finally be left with, we made this one, but you could do the other beta hydrogen, it'd be the same thing. Let's see if we're missing anything. Honestly, for your tests, you're gonna get at least one of these, and I think the most famous one to do is the SOCl₂, SOCl, how you guys say it. SOCl, PBr3, or POCl, pyridine. Those are kind of like famous ones, famous reactions, and so I really think that those would be probably found on the mechanisms in your test. So yeah, make sure to look out for those, and any of the ones with the acids too. Okay, we'll move on to the next one, which is just HCl3. So these are called, let me get my notes out so that I write everything down. This is just hydrohalogenation. And so we start getting into the addition reactions, and as you remember, addition reactions are adding atoms to double bonds, and so this double bond, we're expecting it to go away and be replaced by two other atoms, and honestly, they're just going to be these atoms that they're replacing. The mechanism shouldn't be too hard for these, because again, every time you see an acid, what does it do? It protonates, and so you write your acid out. This is going to be your base, the double bond, and the electrons that make up that double bond. And it grabs onto your proton, and then the leaving group leaves, right? So this follows Markovnikov's rule, and Markovnikov, he says that you're putting the hydrogen in the place that will give you the most stable carbocation. And so you have two options. You have either put the hydrogen here or put the hydrogen here. But putting the hydrogen in this position over here will give me the more stable carbocation, a tertiary carbocation. And so we'll put it right there. And now we're pretty much ready for attack. So we made the electrophile. Our leaving group is pretty good, or it's a nucleophile, and so it goes in and attacks. And so now you have chlorine on one side of it, and I'm sorry, I'm concentrating on something really quick. Okay. Chlorine on one side of it, and then the hydrogen on the other. And so I won't put, I guess I will. I will put stereochemistry, because it's a carbocation, and so you know that you can attack from the front or the back. And so you have something like this. Like that. Those would be your two products. And so some notes for this one is you have carbocation formation. You follow Markovnikov's rule. And again, make sure to say what Markovnikov's rule is. You just put the hydrogen to the least substituted carbon atom to allow for the most stable carbocation. You get racemic mixtures. With stereogenic centers. So only if you created a stereogenic center will you get a racemic mixture. It adds in syn and anti, and I'll kind of explain what that means in a little bit. And of course, if you have carbocation formation, then you can have rearrangements as well. But we didn't have to concern ourselves with rearrangements because our carbocation had happened to be in the most stable position it could be. Okay, so a little side note on what syn and anti means. I'm gonna have this right here. Yeah, whatever. We'll have this right here. Oh, I'm sorry, I'm indecisive. This right here. And we'll do HCl. And so what syn and anti means is that, let's do syn first. Syn means that you're adding the hydrogen and your chlorine in the same position. So like both will be on the wedge. Or they can both be on the dash, so this is still syn. You're adding them in the syn position. Whereas anti means that you're adding them in opposite positions. So one of them could be on the dash and one of them could be on the wedge. This is anti. And so that's all it means. It's how you're adding them on to your double bonds. And so for this top one, HCl, it can be syn or anti. The only thing is we didn't kind of write out the hydrogen, because again, that's what you're doing syn and anti between. You're finding the things that you're adding onto the double bond, but we didn't write out your hydrogens, and I don't think we need to either, just because there's two hydrogens on there. Yeah, I don't think it's needed for these types of reactions, because there's just a lot of ways that they can add on, but at the end of the day, you're always going to be seeing these because these are the only different ones. Because you're always going to be having these hydrogens in the same way. So yeah, don't write the hydrogen out for these. Okay, next one that we'll do is chlorine. So this one is just halogenation. And so you can do halogenation with F2, Cl2, Br2, I2. The only notes that I have for halogenation are anti-addition. So since it's only one of them, I think we can kind of show this. And you are not going to be expecting a rearrangement. Okay. I'm gonna look something up really quick. Just to make sure. Okay, I think I got my answer, but let me just check it one more time. Dang, I don't know why they're making so much noise. The electrophilic halogen. Oh, they're writing on the wall, that's why. Okay, I got my answer. Let me just take one more check. The halogen typically attacks. I'm looking for the mechanism. Okay, well, I know my answer for, Okay, well, for hydrohalogenation over here, pretty sure we will be good. So let me just write a quick note. Okay. For this one up top, what I was confused about was after you make your halogen bridge, which this is how you make your halogen bridge, right? Your double bond attacks chlorine. Your chlorine is also pretty much attacking the double bond and the leaving group leaves. And so from here, you start building your halogen bridge. Which I'm pretty sure, I'm not sure if you guys need to show stereochemistry when you're doing this part of the mechanism, but every time you might write a halogen bridge, they're going to, the two bonds that make up that halogen bridge are going to be on the same side. So it doesn't matter how I choose to write this, either if I wrote these two bonds on the wedge or both on the dash, as long as they're both the same, they'd be fine. I'm just gonna do it like this for now. And we'll see what happens. But this next part that I was kind of confused on was, okay, chlorine already left, and now I'm like, which side is it going to be attacking? The side that's more sterically hindered or the side that's less sterically hindered? And so the reason that I kind of ask myself that is because I have a positive charge on my chlorine, which anytime we kind of form those bridges with a charge, we're saying it's SN1-like, and so you would attack the more substituted carbon, so the one on the left. But I'm not sure if this one is different or not. What I'm going to do for this one is I'm going to attack the less substituted one. So less substituted carbon, and break this bond and put it over here. But we'll ask Dr. Aguilar to make sure of that. But we're going to get the right product for sure. So I have this on the dash, my chlorine stays on the wedge, and since chlorine, this one over here, is attacking from the back, it has to attack from the back, then chlorine has to be on the dash. And so that's kind of why it's anti-addition, because when it attacks my halogen bridge, which should have the two bonds on the same side, it has to be attacking from the back or the front. And so these two things that you added to your alkene, they're going to be on opposite sides of each other, hence the anti-addition. And that's pretty much all you need to worry about. If you wanted to write another product, or I guess you should write another product, because there's two ways that you could have written this original bridge. They could have both be on the wedge or the dash, right? But that means that you'll just get, in this new product, your more substituted chlorine on the dash, and your less substituted chlorine on the wedge, and it's still considered anti-addition. But again, we only showed the mechanism to make one of them, but you get both products for sure. Okay, this next one we do know, and so every time you see chlorine and a double bond, you're going to do that same mechanism where chlorine attacks and the double bond attacks chlorine, and the leaving group leaves, and you're making this halogen bridge. And so I think, again, it would be pretty helpful to write out what that halogen bridge looks like with stereochemistry, just so you know like how you're going to be adding to it. Because I feel like you definitely could memorize this stuff, but if you just understand like the little bits and pieces, it just makes so much sense as to why these notes are relevant, like anti-addition and stuff like that. And so here we did the first step of the halogen bridge formation, but here we have a different reagent, and that's water, and so we have a different nucleophile besides the chlorine that we had originally on J we had attacked with. But here we have H₂O, and so oxygen is going to be my nucleophile, and here oxygen is going to be attacking the more substituted one. And I guess for the reason that we were saying initially, that chlorine has a positive charge on it, and usually we see like oxygens with positive charge on it, and when we see that, we're like, it's SN1-like mechanism, and so your nucleophile would want to attack the more substituted carbon. Okay. And so we're at this point now, where it attacks the more substituted carbon. And chlorine had already kind of broken off. Chlorine will be on the dash. Oops, I did it kind of wrong. So again, since this arrow from oxygen right here is attacking chlorine from the back, then it should kind of invert stereochemistry. So this should be, oh, it would attack from the front. So it'd be on the wedge, and then the methyl group would turn into the dash. So from here, you can get chlorine or anything else that you want to come in and deprotonate the hydrogens, because this is a hydrohalogenation reaction, and so we're expecting to add a halogen and a hydro part, so like the OH part, to the alkene. And so for just this one, we have the alcohol, and we have chlorine where the alkene should have been. But you can also have the stereochemistry kind of the complete opposite. So you'd have two products. I didn't write any notes for this one, but the notes that I would have for this one is it's anti-addition, so we didn't even write that out, but we can notice how we could have just made sense of what kind of addition it would be, because again, what did you add to the double bond? You added alcohol and you added chlorine, and they added in opposite directions of each other, and so it's anti-addition. You're not expecting any rearrangements, however that's spelled, and that's simply because you didn't make any carbocations. And then yes, perfect, H₂O bonds two more substituted carbon. Is it perfect? Okay. Next one that we'll do is HCl reactions. I don't know why I wrote so many HCl reactions, but let us see, because I'm probably trying to confuse you somewhere with this. But we can do this really fast. So, HCl, you protonate it. You have to decide which hydrogen or which position on the double bond you want to put your hydrogen in. And again, you would want to put your hydrogen in a position that will give you a stable carbocation, right? So if I put my hydrogen in that position, I make a secondary carbocation, and since I made a carbocation, I'm like, okay, can I make any rearrangements? And I definitely can, because right next to it, again, you're looking at your alpha and then you're looking at your beta hydrogens. You have a beta hydrogen right here that you can move over. So I'm going to move this hydrogen right here from the bond to the carbon. And when I move that hydrogen, I do my hydride shift. I now have the two hydrogens in this position and a carbocation where the extra methyl substitution is. And so now this is my most stable position, and I'm able to attack with chlorine. And so this would be my answer right here. Dang, they're making so much noise. So I guess the purpose of this is just be very careful with your rearrangements. Try to think ahead like chess. Just looking out for the stability of your final product or your carbocation. Okay, let's see this one. Again, every time you have a acid, see what the heck, you protonate, and you're protonating to get the more stable carbocation. And I'm like, okay, which carbon should I put my hydrogen on? And I'm going to put my hydrogen right here so that I have the tertiary carbocation. From here, there's no other kind of rearrangement that I can make to make my carbocation more stable, and so I immediately attack with my nucleophile, and this is my product. Let's see, do we get... Yeah, and I would write this as straight lines because I don't believe there's a stereogenic center right here, since these groups should be the same. Next one. Are these the same? Yeah, that's interesting. I don't know why I did that, but I guess... Oh, I know what I was trying to do. I think I was trying to do the hydration reactions and stuff like that. We did halogenation, we did halohydrin formation, we're about to do hydroboration-oxidation. I guess this is the one that we're missing. H₂SO₄ and H₂O, H₂SO₄ and H₂O. Yeah, I think that's what I was just trying to do. But again, we'll try to work through these fast. Every time you have an acid, you protonate, decide which side you're going to protonate. We kind of already talked about this, but whenever I make this protonation over here, I get a carbocation in which I can do a rearrangement. And so I do my rearrangement and I get my carbocation in a tertiary position. You don't put stereochemistry wherever you have carbocations, so don't put that on a wedge or a dash. From here, the only thing different is instead of you attacking with chlorine like how we did initially, we have a different nucleophile, and that's H₂O. And so from the nucleophilic part of this H₂O compound, we attack. And so that was a horrible hexane writing, but excuse me. And so again, H₂O attacked, and now you have a good leaving group, but I don't want this to leave, and so what I'll do instead is I'll deprotonate so that I no longer have a good leaving group. But what you will have is this new H group in a position where we did not expect. So again, just make sure to account for rearrangements, because it's not like you could have immediately put the H₂O in one of these positions. Next one, kind of the same mechanism here. Every time you have an acid, you protonate, decide which carbon you want to put it on. I'm going to put on the carbon that will give me the more substituted carbocation, aka the more stable carbocation. So I put it right here. Is there any way for me to make a more stable carbocation? And no, there is not. And so immediately our nucleophile can come in and attack. And so our nucleophile comes in and attack. And we kind of make a good leaving group right here, but I don't want this to leave. And so what I'll do is I will bring back SO3H minus. From one of those electrons on oxygen, I will take away any of these hydrogens and deprotonate. And so my final product will look like this. And I believe there's no stereochemistry here, so just that. So I'll go ahead and highlight my products. Oops. Right here. I apologize for this one for kind of being repetitive. Just going through them really quick and adding some color, because no color hurts my eyes. Okay, and then any notes that I have on this one, let me check. So the only notes that I have for these reactions, I'll write them right here, is that you do form a carbocation, and therefore, if you form a carbocation, look out for rearrangements. These add in syn and anti, so that means that your hydrogen that you added initially and your OH group that you added, they're going to be either in the syn or the anti. When they're syn and anti, though, like any reactions that give you syn and anti, I'm pretty sure you don't have to write the hydrogen that you added initially. So, like, you added the hydrogen right here, so it would have ended up right here. I don't believe you need to write out that hydrogen in syn and anti, just because it would give you like a lot of products and everything like that. So I wouldn't even worry about that when they're syn and anti. But when they're selectively syn or selectively anti, that's when you have to make sure that you write out those hydrogens and the other thing that you added. So syn and anti, rearrangements occur. Markovnikov. So this is a pretty standard reaction. It follows everything that we already knew. Every time you make a carbocation, expect rearrangements. Adds in syn and anti, and if it adds in syn and anti, don't even concern yourself with stereochemistry of what you added to the double bond. And it adds in Markovnikov's way, and so when you talk about Markovnikov, you're talking about acids. So you want to put the hydrogen from your acid in a position, which is usually your least substituted carbon. So you want to put it in a position that will give you the more substituted carbocation, or the more stable carbocation. And so again, that's usually what most of our reactions will follow. Although this last one with hydroboration-oxidation, I believe this one's a bit different. And so I have a lot of notes for this one just because it is so different. And so hydroboration is syn addition. I put oxidation. Occurs with retention of configuration. I'm not quite sure what I meant by that, but I'm sure as we go through the mechanism that we'll be able to see what that means. Results in racemic mixture. of enantiomers. It's concerted addition. I have BH2 goes to least subcarbon. Oh, and I got it. Retention of configuration when OH replaces BH2. Yeah, that will make way more sense. Steric and electronic factors explain regioselectivity. I'm sure they do. I just don't remember what I meant by that. And then next thing I have is that you can see these in a couple of ways. You can see it as BH3, like that kind of, instead of all this. You can see it as 9BN, or you can see it as BH3 with THF. I mean, these are all different ways that you can see it, but they're all pretty much saying the same thing or asking you for the same product. So I wouldn't be too scared if I saw those. Those are good side notes just for the future, like if you take your ACS final next semester, they always do a couple of things like this where you were already taught some kind of reagents and how they're pretty much sorted out, like first you do this and second you do this. But ACS likes to change it up and do things that you may not have practiced with, but do the exact same things. And so just keep that in mind. Next thing we'll do is we will start with the reaction mechanism. So I have this BH2 and I write BH, and so the reason I write that is because your double bond is going to be attacking BH, but your hydrogen is going to be attacking pretty much the carbon on the other side. Again, BH2 is going to the least substituted carbon right now, and so that's why we're kind of favoring certain sides with our arrows. And so this is interesting. And make sure that you check my mechanism on this one because, I don't know, it's just interesting that it does this. So I added my hydrogen on this side, and I added my BH2 on the other, again, to your least substituted carbon. And step 2, which is all I have, because I'm pretty sure they don't show us the mechanism for this step 2, is it just gets replaced. The BH2 gets replaced. And so I'll write the basic structure of both of the compounds that I'm expecting. The reason I'm writing 2 of them is because I'm expecting syn addition, so there's 2 ways that I can add it. So one where my hydrogen is on the wedge, and then my OH group that again replaces BH2 in this second reaction. Those are going to be on the same side, and therefore the rest of the compound is going to follow along. And these, again, they have to be on the same side since they're syn addition. And then the rest of the compound follows along. And so these would be my 2 products of syn addition. Again, syn addition just meaning whatever you're adding to the double bond, it has to be on the same side. So you're adding OH group and you're adding a hydrogen. And so they have to be on the same side of the products. Yeah, and that's pretty much all I have for this worksheet. Sorry that it was so long. If you have any questions on any of this, I kind of made it messy because I was trying to write fast. If you have any question on this, please let me know. These are pretty much all the notes that I made for my 4th exam when I was in OChem 2, and they really helped me because even though you're not going to do all of these mechanisms on the test, the mechanisms kind of help you determine, okay, is it E1 or is it SN1 and stuff like that. Do I have to do any rearrangements? And you just start catching on to these things without having to memorize, oh, this is E1 when this, it's E2 when this. There's some that like are forced, like how this one is E2 no matter what. There's some of those that you're just going to have to memorize, and I'm pretty sure, I mean, just off the top of my head, it's going to be like SOCl₂, that's forced SN2, PBr3, that's a forced SN2 mechanism, and POCl₃, that's a forced E2 mechanism. So those things, I think, are good things to memorize, but everything else I feel like goes according to what we expect, again, besides this last one as well, because that one kind of goes with, like, kind of anti-Markovnikov. So yeah, just account for the very, very different reactions. And then the rest of them, just make sure that you find your patterns. If you find an acid, protonate, stuff like that. Okay, so hopefully this helps you guys. If you guys have any questions, please email me and we'll try to get back to you fast. And if you do choose to email about the exam review or any question, honestly, please CC the whole team. So like CC me, CC Noah, CC Dr. Aguilar, whoever you want. Just make sure that everyone is on that email. Thank you guys.